For this NMR, the molecular formula is C9H10O. Let's go ahead and calculate the hydrogen deficiency index. So if we have 9 carbons, the maximum number of hydrogens we can have is 2 times 9 plus 2. And 2 times 9 plus 2 is equal to 20. So for 9 carbons, 20 hydrogens is the maximum number. Here we have only 10 hydrogens. So we are missing 10 hydrogens, or we're missing 5 pairs of hydrogens. Therefore, the hydrogen deficiency index is equal to 5. With an HDI of 4 or higher, you think benzene ring. So I'm going to go ahead and draw a benzene ring in here because I'm pretty sure there's one in our molecule. And if we look down here for this very complicated looking signal, right, it's really a bunch of overlapping signals from protons on the benzene ring. And I know that because we're in the aromatic proton region for our NMR. Right, so right in here. So I have 5 aromatic protons. Let me go ahead and draw them in. So I put my 5 aromatic protons in slightly different environments, giving us overlapping signals, which give us this complicated looking one down here. All right, that takes care of an HDI of 4, but we have an HDI of 5, so we have one more thing, and it's of course going to be a double bond. And I know that because of this signal down here between 9 and 10. Remember, a signal between 9 and 10, that's the region for an aldehyde proton. So we have an aldehyde proton over here. So I draw in my carbonyl, I draw in my hydrogen, and then this is another piece of the puzzle here. So this aldehyde is connected to something. All right, let's go to these other 2 signals down here. So this signal represents 2 protons. So I'm going to write a CH2 here. How many neighboring protons do we have for those 2 CH2 protons? Well, there's 1, 2, 3 peaks. So if there's 3 peaks, just subtract 1 to figure out how many neighboring protons you have. So 3 minus 1 is equal to 2. So this is a CH2 with 2 neighbors. It's the exact same thing for this signal, right? So this represents 2 protons, so this would be a CH2. And once again, we have 3 peaks, 1, 2, 3. So 3 minus 1 is 2. So this is a CH2 with 2 neighbors. And so these 2 CH2s must be right next to each other, right? So let me draw that out here. So if we have one CH2 next to another CH2, each of those CH2 protons have 2 neighbors. For example, if I think about these right here, right, how many neighboring protons? Well, this is the carbon next door, and I have 2 neighboring protons. So that makes sense when we look at the signal on the NMR. There's only one way to put together these different pieces of the puzzle, right? So we would have to put a CH2 coming off this place on our benzene ring, and then another CH2, and then finally our aldehyde. So go ahead and draw in our aldehyde like that. And so that must be the structure of our molecule. So a little bit about this aldehyde proton. Let me go ahead and highlight it over here. So this aldehyde proton right here, we only see a singlet on the NMR spectrum, but it does have 2 neighbors, right? So let me go ahead and draw in the neighboring protons. So they're on this carbon right here. So if we're thinking about the aldehyde proton, right, this is the carbon next door, and so we have 2 neighboring protons. And with 2 neighbors, you might think we would get some splitting for the signal for this aldehyde proton here, but we don't notice any on the NMR. And normally you don't see any splitting because the coupling constant is usually very small, and so therefore the signal looks like, often it looks like it's a singlet, but sometimes if you zoom in, you can observe some splitting for the aldehyde proton. For this NMR, we have a signal for 2 protons, so that must be a CH2. And how many neighboring protons? Well, for this signal, we have 4 peaks. 1, 2, 3, 4. So 4 minus 1 is 3. So 3 neighboring protons for these 2 CH2 protons. What about the chemical shift for this signal, right? So the chemical shift is getting close to 4 parts per million. And in that range, that makes us think about those protons being bonded to a carbon that's bonded to an electronegative atom. And if we look at our molecular formula, the only electronegative atom we see on here is oxygen. So that oxygen must be bonded to this carbon. So let's go ahead and draw that. So that oxygen is bonded to that carbon, and that carbon is bonded to 2 hydrogens. So that's what we have so far. So the oxygen, right? The oxygen is more electronegative than carbon. The oxygen is withdrawing some electron density from these two protons and giving us a higher value for the chemical shift. All right, so the signal for these two protons in magenta is right here. Next, let's look at this signal. So we have 3 protons, so a CH3. How many neighboring protons? Well, for our signal, we see 1, 2, 3 peaks. So 3 minus 1 is 2. So 2 neighboring protons. And so 2 neighboring protons must be the ones in magenta, right? So we can go ahead and put our methyl group on here. And let's use red for the methyl protons. So these 3 methyl protons are giving us this signal, right? We predicted 2 neighbors, and those neighboring protons are the ones in magenta right here. So those are the 2 neighbors. For the ones in magenta, right, we predicted 3 neighbors, and so that's 1, 2, and 3. Finally, let's look at the last signal, right? So we only have 1 more proton to think about. There's only 1 place to put it, right? It must go on the oxygen. So this is the NMR spectrum for an alcohol, for ethanol, right? So this proton in blue is this signal on the NMR spectrum. And the chemical shift is hard to predict for an alcoholic proton. Right, usually you see 2 to 5 parts per million, but it's really hard to predict exactly where this signal is going to appear. And also, let's think about how many neighboring protons this proton in blue has. Right, so the carbon next door has 2 neighbors. So you would expect 2 plus 1 peaks, right? If n is equal to 2, 2 plus 1 gives us 3. So we'd expect a triplet for this signal, but we only see a singlet. And that's because this proton, this alcoholic proton, rapidly passes from one molecule to another. And this proton transfer is so fast that the proton never stays in place long enough to interact with these neighboring protons. And so the NMR machine usually doesn't show any splitting. Under the right conditions, it is possible for splitting of the alcoholic proton to occur, and you might see a triplet here. But on most NMRs, you're only going to see a singlet, which is another clue on your NMR spectrum.